6 over here, and we're looking at the chain rule. Okay, what is the chain rule? The chain rule, we use this when we want to find the derivative of a composite function. Okay, so let's think of a composite function. Let's just say f of x is a composite function. It's actually equal to g of x composite h of x. Okay. And g of x and h of x are smooth and continuous. They're locally linear and they're differentiable for their domain. And another way of writing this actually is to say g of h of x. And that you can sort of see the nesting of the composite function. So if we want to find the derivative of our composite function, f of x, with respect to x, what we need to do is first take the derivative of the entire composite function. I'm going to grab it, g of h of x, let me copy it. We're going to take the derivative of g of h of x with respect to the input into the g function. So we're going to take it with respect to h of x. So let me copy that. So it's like we freeze h of x like it's a giant variable, and we're taking the derivative of g of x with respect to the h of x function. And then we multiply this by the derivative of the h of x function with respect to its input, which is x. Okay, so thinking about this again, let me get my highlighter out here, is that when we're finding the derivative of f of x, and f of x is a composite function, first we find the derivative of the outer function, g, with respect to its input, and here's its input. So the input is h of x, so it's almost like h of x is a variable, and we're taking the derivative with respect to this entire frozen variable. And then we take the derivative of the h function with respect to its input, which is x. So when you're finding the derivative with a chain rule, you keep finding the derivative with respect to the input of the function, and then you multiply it by the derivative of the next function in with respect to its input, and you keep going until the derivative is with respect to x. Okay? And so let me give you an example of this, because you could actually have a triple chain, and we could have more than one function there. We could have we could have g of h of k of x, right? And keep going. So let's say f of x is a composite function, and it's equal to the cosine of x squared. And this is definitely a composite function, right? Where if we were to say that this is the composite of g of h of x, in fact, if this is how we're looking at it, well then the g of x function is the cosine of x. That's the outer function. And the h of x function is x squared. And we happen to know that both the cosine of x and x squared are smooth continuous functions. They're differentiable for their domain. So let's go ahead and find the derivative using the chain rule. So if we want to find the f prime of x, which is the derivative of f with respect to x, we are going to take the derivative of the entire thing, the cosine of x squared, with respect to the input to the cosine function, so with respect to x squared, all right? That's our first bit. So the input is x squared, and that becomes our variable. Well, you could think of it as a frozen variable because that's with respect to this, okay? Times the derivative of the inner function, which is x squared, with respect to the input to this function, which is x. You input x and you square it, okay? So here the input itself is just x, and with respect to x. So what is this equal to? Well, the derivative of the cosine is the negative sign. So it would be a negative sign of the input, which is x squared, times, and the next piece, which is the derivative of x squared with respect to x, is 2x. And so if we simplify this, we end up with a negative, or sort of clean this up a little bit, negative 2x sine of x squared. So that's our example of when we have two functions, or a composite of two functions. Let's try another one. Let me give you another one, and then we're going to look at it when we have a composite of maybe three functions. Okay? So let me add a page below. Do you have a question over there? Are we okay? You are? Okay. And I'm going to stop the video and we'll have some more questions in a minute. Okay, so let's try another one. Let's say we have f of x is equal to the cosine. Let's do sine this time. The sine of, let's say this one is x cubed. And I want to cube the sine. I'm going to cube it. So sine cubed. And I want to find the derivative. This is actually the composite of three functions, right? This is the sine cubed of x cubed. And another way to write this, now I wrote it the way it's generally written in mathematics, but another way to write this is to say, well, this is actually the same thing as the sine of x cubed all squared. All cubed, I'm sorry, all cubed. Okay, so normally we see it written this way. But when we're thinking about the chain rule, sometimes it's better to rewrite it so that because the cube is done last, so put the cube on the outside, okay? So let's go ahead and work out how would we determine f prime of x. Let me get this. Oops, I've got highlighting in there. Okay. So f prime of x is equal to the derivative of, and I'm going to go grab this whole function the way I rewrote it. Let me copy it. Just appears while I copy it and paste it. There it is, and I'm going to take its derivative with respect to its input. Well, it's the input into this is the sine of x cubed. The outer function is a cubic, right? So you can see the input actually is the sine of x cubed. That's the input. So we're going to take the derivative with respect to the input. So when you think about that, like the input's sort of frozen, and you're going to use the power rule, freezing that. And then this is going to be times the derivative of the input, which was what we see down here. Take the derivative of that, right? So of the sine of x cubed. And in this case, the function, the outer function, is the sine function. And we want to take the derivative of this with respect to its input, and its input is x cubed. So x cubed is the input, and so we sort of freeze x cubed and treat it like that is our variable. And now we take the derivative of this one here, that function, which is a cubic again, and that's x cubed. And the input to the cubic function is x. So we're taking the derivative of x cubed with respect to x. And what do we get? Well, in the first case, it's a cubic, right? So we use the power rule. So 3 comes down to the front, and then our frozen sort of mock variable there, which is sine of x cubed, is here. And this now becomes raised to the 3 minus 1, which is 2, right? And so, in fact, if we're talking about a sine, the 2 would go here. That's just standard procedure for a trig function, is that you put the degree that you raise it to right after the trig function before the input, right? And then this is multiplied by, and now we're going to do this one right here. Now this one is a sine function, and the derivative of the sine is the cosine. So the derivative of the sine of x cubed with respect to x cubed is the cosine of x cubed. So that's our next one. So we put cosine of x cubed. And then the last one right here is just the derivative of x cubed, which becomes 3x squared. 3x squared. So here you have it, but we're going to need to clean it up. So we take all of our sort of coefficients to our 3 different facts we have here. 3 times 3 is 9. And we would usually move that x squared up to the front times the I don't have to have cosine first, but I am writing it first. That's fine. Cosine x cubed times the sine of squared of x cubed, and this was a triple chain, and it's an example of the chain rule. There's our answer. So I'm going to stop the video and we're going to try some practice problems.